Hey guys, this is lesson 8.8 for exponential growth and decay. So make sure you title your paper. Now, exponential growth, it's the same equation that we use for an exponential function. This same equation, however, if you notice, A is greater than 0 and B is greater than 1. So A, you'd have to start at 1 and you could triple or quadruple, or it's getting bigger. So the base, remember, is your growth factor. That's how much you're going to go up by. So, modeling exponential growth. Since 1995, the daily cost of patient care in the community hospitals in the United States has increased about 4% per year. In 95, such hospital costs were at an average of $968 per day. So, they have an equation, and you're going to start here because this is what you're starting with, 968, and it's going up 4% a year. Now, the growth factor is 4%. However, if you just times 968 by 4%, it would be a tiny number. So really what you're doing is you're timesing it by 100% plus an additional 4% because it's increasing. So you're going to start with what you have, which is your 100%, and it's going up an additional 4%. So what happens is you get 104%, which is a 1.04 multiplier, kind of like in the problems we did previously with the animals, and they were tripling or quadrupling. Instead of putting a 3 there for tripling like that, they do the growth factor, which is 104%. So then what you would do is you would say, okay, so 1995, if I wanted to go to 2010, then you would add the 15 years as your exponent, and they did that down here. So we're going to try this problem. Suppose your community has 4,512 students this year. The student population is growing 2.5% each year. Write an equation to model the student population. And what will the population be in 3 years? So try this problem. Okay, so my equation is y equals 4,512 times 1.025 to the x power. So that's my equation. And what I'm going to do to solve it is I'm going to put 412 times 1.025 to the third power. So 1.025 to the third power is 1.076, and then you times it by 4512. So my population is going to be 4858.9, and then we always know with students you're going to round up, so it would be 4859 students. 4,859. Okay, when a bank pays interest on both the principal and the interest an account has already earned, the bank is paying compound interest. So now they're bringing up compound interest because it is an exponential function. So they're talking about compound interest because your equation is going to look very much the same. An interest period is the length of time over which interest is calculated. So that's kind of just a refresher from last year. Suppose your parents deposited $1,500 in an account paying 3.5% interest, compound annually once a year when you were born. Find the balance after 18 years. So you're going to use an exponential function to compound interest. So if you ever want to work in a bank or any of this, you'll be using these functions daily. So here's my equation, y equals 1,500 times 1.035, because that's my interest, and then to the x power. So you're going to put it to the 18th power, and then you would have $2,786.23. So that's pretty good. So try this problem. Suppose the interest rate on the account in example 2 was 4%. How much would be in the account after 18 years? Just try A, and then we'll go over it. Okay, so I'm going to change my equation. So it's going to be y equals 1,500 times 1.04 to the 18th power. 1.04 to the 18th power is 2.02 times 1,500. So your balance would be $3,038.72. So it says another formula for compound interest is B equals P. This is what we used last year. The balance equals the principal times 1 plus the rate, where B is the balance and P is the principal. So just make sure you know that. All right, compound interest. Suppose the account in example 2 paid interest compound quarterly instead of annually. Find the account balance after 18 years. So compounded quarterly means 4 times a year. So you're going to have to do the 3.5% divided by 4 if you remember this. So here's my equation. So there are 4 interest periods in 1 year. So you have to divide the interest into 4 parts. So they did that, and they got 3.5% divided by 4, and then they got 0.00875. And then for your exponent, remember, you have to times that by 4, because it's not going to just be 18 years. You wouldn't just put in an 18. You have to put in a 72, because there's 72 periods within 18 years. So then the balance after 18 years will be 2808. All right, the graphs at the right show exponential growth and exponential decay. For exponential growth, as x increases, y increases exponentially. So this is exponential growth. They're both starting at 2 and they're going up. For exponential decay, as x increases, y decreases exponentially. So it's going to go down, and like I said before, you're never going to quite reach the 0, the x line. So it just goes right along the bottom and just keeps getting tiny, tiny, tiny. So exponential decay, here's the equation for that. Now if you notice, the starting amount is greater than 0. So A has to be greater than 0. Okay, when x equals 0. So this is when x equals 0. A is going to be a number greater than 0. It has to be like 0.5, 1, 300, 1752, whatever. And then the base is going to be a number between 0 and 1. For something to go down, for it to decay, it has to be less than 1. Because we know if you do 5 times 1, it's 5. But if you did 5 times a half, that's 2.5. So it has to be less than 1. So in 1990, the population of Washington, D.C. was about 604,000 people. Since the population has decreased about 1.8% per year. What is the initial number of people? So that's your 6,400. So you're going to start your equation with that, with A, 604,000, sorry. Okay, what is the decay factor? Well, the decay factor is 1.8%. Now, you're not going to put in 1.8%. You have to start at 100, remember, and you have to minus 1.8%. So really, that number is being multiplied by 98.2%. So if I were to write that, it would be 0.982. Because remember, it has to be a number between 0 and 1. So that's 0.982. So that's the decay factor. Write the equation. So here's my equation, and then I have it to the x power. And then it says, suppose the current trend continues. Predict the population of Washington, D.C. in 2010. So that was 1990, and then they want me to go to 2010. So this would be 20. So if I do this, I do 0.982 to the 20th power, and then times that by 604,000. The population of Washington, D.C. would be 420,016.8, which you would round up 420,017 people. So if it's decreasing, they are losing, in 20 years, they lose 180,000 people, roughly. All right, that's it for your notes.